Welcome back, my fellow duplicants. Today we're going to be playing around with rockets in my oxygen not included test lab. So today I want to test a couple of things. One, how hot does the exhaust from the hydrogen engine get? How hot is the exhaust from the petroleum engine? And what can we use that to kind of affect? So the first thing I also wanted to understand is how deep the flame penetration is from one of these rockets. Okay, so how am I going to test that? Well, check this out. So right down here, I have several obsidian tiles. In between that, I have an insulation tile. So when we run this engine, we will see a visual indication of where the stuff gets hot. So the energy from this tile, for example, can only go up, down, left, or right, but it's flanked on every side there by insulation, which is, you got the thermal conductivity of nothing. It cannot transfer heat from here to this tile, so we don't have to worry about that. So we should be able to see just how hot each tile gets. So what I hope to gain from this experiment is an understanding of how many tiles I need to go down in order to protect anything that might be down here, and also to give us some sort of target for how large of an area I want to capture heat from something like this hydrogen engine or the petroleum engine. So let's start off with the petroleum engine here. Okay, so I have two rockets here. I have Patronus, which is obviously petrol, and then I have Hydronus, which is hydrogen. All right, so let's give Brian his launch codes here and activate the flight control system. We will now see the doors open, the launch pad clear, and the rocket fire. Boosh. Yeah! Get some of that. All right, let's take a look at the heat. See what I'm talking about? Ooh! Look at that. Successful experiment. Ha-ha! Except for it looks like it needs to be a little bit deeper. All right. All right, experiment number 2. Let's go ahead and launch this rocket to see just how deep it goes. We are now 17 tiles deep. Yeah! Oh, I love rockets. All right, slow it down. Look at how hot that is, by the way. Look at that. I saw 1,475 degrees Celsius. Oh my gosh, 1,005. Look at that heat, 1,800. So hot. Melted steel, but from where? Oh, well, okay then. Wasn't supposed to do that. Okay, never mind that minor disaster. It's all right. It's okay. Let's clear this floor. Let's see what we have for temperatures down here. Well, this tile, 1,900 degrees Celsius. That's hot. Okay, so you can see just about everything on top here got exposed to a decent amount of heat. However, the heat only penetrated 9 tiles down and 3 wide. So it's 9 by 3. You have to keep that in mind, at least when dealing with the petroleum rocket. Okay, let's try the hydrogen rocket. Go ahead and flip the switch on that one and see what happens here. Aha! What? You're going to hit the doors again. What happened here? Never mind about that. Okay, let's see just how deep the flames go. There we go. We destroyed the bunker doors yet again. So the answer here is 9 by 3. So it's the same for both rockets. Okay, so if I wanted to capture heat from this, what I need to be aware of is just how deep I need to go right down here. So that's the flame path right there. Well, the flame is right here, and then I think you just get the gases that are blowing off the thing. So what we should be able to do here is use something like diamond in order to absorb a decent amount of energy and then use that to transfer it into something else. Okay, so we have a specific heat capacity of 0.5 with a thermal conductivity of 80. There's also other materials we could use as well, such as steel is readily available. I think tungsten can deal with the heat, maybe. Let's see here. Yes, 3,000 degrees. Steel is 2,400. That actually might be... that might be kind of low for the hydrogen. Let's see. Let's launch both of these rockets now. And we'll see just how hot this window tile gets down here. Boosh! All right, let's take a look at the heat. Bam! Rest in peace, doors. Like, they might as well just not even be there. Rocket apparently doesn't care about them. Temperatures. What do we have here? At the top, right below the rocket, was 445. Right here, I have 896 degrees. Now, because the thermal conductivity is so high in this window tile, man, it just transfers the heat around like really good. So let's see where it stabilizes. All right, surprising. Over here on the left, the window tile, it's going to stabilize at about 380 or so. Or the one on the right is 680, more or less. It kind of depends on where you measure it. It'll take a little time for that. Well, it pretty much will never even out. Let's just go with this tile right here, right? 700, here, this one's in the middle. 685, 389. All right, so if you're thinking to yourself, well, how in the world am I going to manage to deal with something that's 400 degrees, let alone 600 degrees? Because if we take a look at what we have for materials over here, supercoolant comes to mind. Now, the problem is that supercoolant turns into a gas at 400 degrees Celsius, which isn't really a convenient number for the temperatures that we're dealing with, because there's a very good chance that we're going to go below 400 degrees Celsius. And while it has fantastic properties, almost ridiculous, 8.4 DTUs heat capacity and 1.2 thermal conductivity, there is a new gas in the game that will work perfectly for our needs. And despite its image here, it's actually green. That's right, ladies and gentlemen, it's ethanol gas. Specific heat capacity of 2.1 with a thermal conductivity of 1. Beautiful! And it turns from a liquid into a gas at 78 degrees Celsius, well below any of the temperatures that we're going to be dealing with. So that right there is what we're going to be using to convey thermal energy from up here down to, well, a couple of different devices. All right, so may I present to you two different options here. The one on the right is going to extract electricity from heat, although you would need to provide a method for cooling the steam turbine. I'm just using a massive amount of oxalate just for the sake of it. But essentially what this is doing here is that it has a heat loop that's running up through the window tiles up here, which is where all of the heat's going to be. And then it's bringing that back down here to these window tiles below. So this just provides a very simple way to continuously move heat from up here to down here. The automation is handled via this little temperature sensor right inside of here. So this is just looking for anything that is below 195 degrees. At that point, these thermocoupler doors essentially are going to be closed, and that's going to take the heat from down here into this metal tile up here into all of these temperature shift plates, which I've made out of diamond, and then that will run the steam turbine. You don't necessarily need the temperature shift plates. It was just fancy, so I did it. The main idea is that you're going to use the doors in order to keep the temperature nice and low so that the steam turbine doesn't overrun on its temperature and you don't end up wasting a bunch of energy by producing extra heat on the turbine itself. So it really doesn't matter how hot the stuff is up here so long as it doesn't actually melt the pipes. You do have to keep that in mind. For this test I'm using thermium because it goes up to 2,600 degrees Celsius. Steel goes up to 2,400, so that's also a much more available, shall I say, material to use. This thing puts out a lot of heat. I don't think it'll put out enough heat to actually destroy it, though. Now, the more interesting machine here is the one over here on the left. So what this is going to do is it's going to convert crude oil into petroleum by using the waterfall method. And it's using a similar automation setup to where I have the heat being piped from up here down here. So we're using heat pipes. And then I use thermocoupler doors in order to transfer the potential energy out here into all of this down here. And that's actually where it's going to do converting. And what I've done here is I've included some ethanol gas that should help with the thermal transfer that's happening inside of here. And it should maintain a temperature that's so hot that we don't have to worry about that turning into a liquid and ending up inside of our pump. Even if it does end up inside of our pump, I have a liquid filter that will filter that out. Mind you, this is something that would also require cooling. In my example, it's just chilling down here. So anything that is not petroleum gets piped back in over here on the left and recirculated. So the automation for this is just handled by this little thermal sensor over here. This is looking for anything that's below 450 degrees Celsius. And at that point, the doors will close and the liquid shutoff will shut off so that we don't bring more oil into here. So we'll just kind of see how this works. I haven't tested this one just yet, but I think it should work out pretty good. Okay, so let's fire up some rockets and see how this thing runs. We'll be launching both of these at the exact same time. Whoosh, come on. Oh, yeah, that's right. I put it on a filter gate. Of Of course, I might want to use bunker tiles down here because I'm seeing meteors drop down. And that would actually damage these window tiles. So maybe that's the first thing I change, because it could potentially happen where that would drop right down there, and that would be a problem. Anyhow, let's not worry about it. Both of these rockets are ready to rumble. Boom! Look at that heat! Awesome! Alright, so both of those have launched out of there like they launched out of there. Hey, meteor, stop pointing out the obvious. Alright, so the temperatures are now incredibly hot up here, right? We got 400 and some, 600 and some. So that means by the time we get back down here, we should see these temperatures start to climb. So it's coming in at 500 degrees and it's leaving at 113. Same sort of deal we're coming in at. So we're definitely generating some power over here. Beautiful, good to see that. So I can see here that it's taking a while to wick all of the temperature out from here down to here. That's kind of a ways to go. This is actually going pretty quick though. You see it's dropping. We're down to 500 degrees over here. This thing's actually running pretty good. This has a lot of mass down there. I'm not 100% sure that that's actually going to work, but... So the reason I'm curious about this one over here on the left a little bit more is because it's... I'm thinking a good amount of the rockets I'm going to launch are going to be petroleum. Just the way it's set up in my base, since I have a leaky oil fissure, not to mention you can get your hands on a decent amount of it. Whereas the hydrogen probably isn't going to be launched as much. So I'd like to be able to see if the petroleum rocket over here is capable of heating its own fuel or converting its own fuel. Now this is at the preset temperature of 300 degrees Celsius, which is 50 underneath what I would be getting out of my leaky oil fissure, which is I think 350 degrees Celsius. So it doesn't have a huge amount of temperature that it has to increase. But it is, we're talking 100 degrees Celsius there. So you can see here it goes from crude oil to petroleum at 400. So yeah, we'll see. All right, incoming rocket. Ooh, and you know what's cool? The second time the rocket flies in, we will actually get a second burst of heat. And a second punishment of meteors. Thank you, game. Oh! Good job, Jen. Keep working on that tile. I didn't think about that. I only thought about the launch. But no, you get blasted twice. So this thing's up to 200 degrees. So just about everything down here looks kind of averaging out at like 200, I should say. Anywhere from 170 to 200. And that was just from the launch. So this is the return. Oh, here comes the second one. Oh, yeah! Both them rockets are coming back. Interesting that this one detected it sooner. Whatever. Rest in peace, doors. Oh, man. Come on now, that's rude. What did those doors ever do to you? Anyhow, here we go. Boom! Take that. Look at all that heat. Yeah, that definitely is legit. Look at that. We're right up to 700, 800 degrees. 900? Almost 1,000. Excuse me. Whose job was it to fly Hydronus over here? Ashcon, come on, man. You broke the doors. I need like turbo doors or something. All right, well, I'm not worried about the steel here, so let's just get rid of that. Let's just see what happens down here. So this is 144 degrees Celsius, even though it's incredibly hot up top. Okay, so one thing that's probably going on here is I can only transfer so much energy because the gas pipe only contains 1 kilogram of ethanol gas, whereas liquid is 10 times as much. So it might be that I want to run multiple actual pipes in order to make that thing operate. But anyhow, there we go. We're launching it up again. Doors? Okay, they're open. Thank you. Boom! No. This tile is getting absolutely 1,500 degrees. Okay, what is the temperature of the steam right there? 1,800, 1,900, nearly 2,000 degrees. Whoa, here we go. There goes the next rocket. I love this. Is it enough to run the steam turbine at 800 watts or 850 watts? Yeah, looks like it is. So this is actually looking for above 195, whereas this is looking for above 450. Sorry if I said that wrong previously. Look at that. Boom. Just about 850 watts. Okay, so that is working. Even though it is only 1 kilogram, ethanol is proving its worth here in that it can actually move a fair amount of energy between one area and the next. Nice. Very nice. Although that is also in part to the ridiculous temperature that it's running at too. 1,000 degrees Celsius. So, yeah, you can do that math if you really want to. It's the weekend. I'm not going to worry about it. So the rocket over here on the left has a much harder job in that it's attempting to heat up all of this. So, the thing is I couldn't just string these together because then I would only have 1 kilogram of gas moving for both systems. I would actually cut the energy in half. Well, the flow in half. All right, we'll let it run a whole lot faster here. See if the system over on the left ever catches up or if I have to use multiple rockets to heat it up. I didn't put as many temperature shift plates in here, just a few. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe more than just a few. Put 9 in there. Not to mention a bunch of tiles. Don't worry about it. It'll be fine. Aha! This time we have detected Hadronus. But I'm a little worried about this scan over here. Okay, good. There comes the other rocket. Nice. Okay, well, apparently, this thing's just going to launch like crazy. Open up doors! Open up! Ah! Okay, so that thing constantly has enough fuel to keep running to like the nearest spot. So it just keeps running to the nearest spot. All right, so I caved and I put bunker tiles up here because that's what you would actually have if you were to build this in a game, because you want the bunker tiles to be able to take the meteor strikes. Otherwise, you end up breaking the window tile, and that's just no fun. Okay, and I somehow glitched out the fuel. Apparently, I didn't like landing a rocket and having it automatically launch. Boosh! Okay. Quality. Boom! All right, there we go. Intensely bright. No, 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 stop. Boosh. Hey, see, that's what the button's for. Cargo bay. Thank you. Now, get to launch. Oh no, the doors, the doors. In case you're wondering, this system over here on the right is maintaining enough energy to run this steam turbine continuously without much of a problem. But then again, it is launching over and over and over again. And I doubt you would launch a hydrogen rocket over and over again this fast. I mean, maybe. It's only going to a 10,000 kilometer asteroid. I would think if you're going to run something like that, you might actually be running a little bit further. But who knows, maybe there's something really cool here and you just want that. If your goal is just to make something incredibly hot in your base, something that you can melt stuff down with or whatever, then actually running to 10,000 and back, if you actually find some like decent materials here, then maybe that's actually not a bad idea. It's fairly efficient. It doesn't cost too much fuel. And you get that first burst of heat, and then it turns around and you get another big burst of heat. We have this high-tech rocket, but our dupes still can't pee. They literally come back and they run down to the bathroom, and then they run back up, jump in the rocket, and go off for another several cycles. Dude, just pee out the window. It'll be fine. Nobody's looking. I mean, that's exactly how NASA does it. I watched Apollo 13. Did you see that? Did you see that? Let's slow it down. Boom! Oil to petroleum. Boom! Just like that. Look at it flow. Man! Now how long is it going to take to heat back up? Okay, not bad, not bad. Let's just watch it in normal speed, which is 3x. Boosh! Oh, nice. Nice! Okay, so one thing I want to do here is I'm just going to put a little bit of a... Whoops. I'm just going to put a little filter gate on this. Get out of there, Steel. You're not welcome. Okay, so that'll keep the doors closed for just a little bit longer. Boosh! And then it's going to run again. Yeah, buddy! From rocket fuel to rocket fuel. The cycle of life. And how much have I converted here? 75, 75. Ooh. I think I've converted... By the time this thing gets back, there's a good chance I'll have converted enough petroleum to fire it up again. And there's also a good chance... that I'll have generated enough power to maybe make my own fuel. Well, that thing's been... There's something... There's a lot to this. Look at it. Look at it go! Dude, that thing's running a lot. Look at it. So the doors only flick for just a second here, so maybe we set that to like, I don't know, 10 seconds. Maybe we don't even have to worry about it. Well, yes, I guess we do have to worry about it. It might get too hot if I'm not running crude oil. Psh, that thing's working great. How about that? Okay, does it work at a lower temperature? How about 425? Whoa, game. Okay, so there we go. It is just converting like crazy. So there we are. We're now down to 425. This is fantastic. Okay, so what are the temps like? Here, oh, look at this. So this one's at 610, and this one's at 630. Okay, so it works at 425, which is nice. It doesn't look like I'm getting any... No, I'm not getting any oil out of that. All right, so what about 415? How close to the edge can we run? So, I mean, obviously, the less we heat it up, the cooler we can run this chamber, the better off it'll be. Hey, look who's back. What is with bringing back blenders? Everybody keeps bringing me back blenders. What do you have to do? Go get another blender? Seems to be working just fine at 415. 405. I'm gonna run it right on the edge, people. Right on the edge. Look at this thing. It's working. It's working at 405. You can see that they end up with a little bit of crude oil. Makes it down that far, but then it converts. So it's not a big deal. By using the waterfall method, what we're doing is we're really splitting up the mass of the petroleum into smaller pieces. Therefore, we can change the temperature of that much, much faster. And since that is also being, landing on a tile that has thermal shift plates by it and is also flanked by a very conductive gas, which is ethanol gas, we're able to change that temperature very, very quickly because it's not a lot of mass and we have lots of thermal conductivity all the way around it with a high enough thermal mass behind it to where this stuff doesn't really change in temperature all that much. So this becomes very predictable, even though it's very, very close to its transition point, which is just 405. That's awesome. That means it's nice and efficient. Now it doesn't seem like it's running all that much more, but essentially we're conserving more thermal energy up here, which means we could potentially run more liquid. I guess there is only one true way to test this. What we'll do is we'll just run this, and this will become my only source of fuel for the petroleum rocket. Although I have no doubts that it will actually be able to heat up its own fuel. However, let's increase the challenge here for our converter. Rather than bringing in the crude oil at 300 degrees Celsius, we'll bring it in at 100. Okay, so here we go. Now the crude oil has made it down this far. But you know what? It still flashed over to petroleum. However, it did drop the temperature down a little bit further, so it doesn't look like it's running quite as much. I'm a little bit worried that we might end up with crude oil at the bottom. It's only entering the system at 100 degrees. This is not thermally conductive at all. I'm using insulation down there. Yeah, it's working out great. One thing I could potentially use is down here is a little hydro sensor. If I just make sure that all of that is petroleum on the bottom, there's a good chance that crude oil would actually sit on top and disable this. Bam, there goes that rocket. I also suppose you could just use this as a tank for petroleum and just store it at like 400 degrees. Really cool. I like that. All right, so here we have it. In concept, this works out really quite well. We heat up the bunker tiles up top, and then we have the window tiles down below, and we run basically a heating loop right through this. Down here, this little arrangement here seems to do really good at converting crude oil into petroleum, and it looks like it converts more than enough petroleum to refuel its engines for the next flight. Over here, the same sort of thing, but running with hydrogen, although it doesn't necessarily need to run with hydrogen. Heats up the tiles, and we are extracting a good amount of energy from them and converting that into electricity. So there we have it. It works in concept. I'll have to throw it into my super dupe mega base just to see how it works out in a real game. Thank you guys for watching. Hope you guys have enjoyed this episode here of Oxygen Not Included. If this looks like the channel for you, maybe consider hitting that subscribe button. As always, stay awesome. Peace. Mr-Brothgar out.